Hello. Summary questions 1.2. Question 1. Which force, the strong nuclear force or the electrostatic force, A, does not affect a neutron? Okay, well, an electrostatic force is only going to concern itself with particles that are charged, and a neutron has no charge. Therefore, the force that does not affect the neutron will be electrostatic. As no charge. B, has a limited range. So the nuclear force, electrostatic force has limited range. Well, we know that the electrostatic force, in terms compared to particles, is actually got quite a good range to it. If it didn't have, then we wouldn't have things being held to the wall by static electricity, etc., etc. So we should also know, from having read the textbook, that the nuclear force is a very, very limited range, only to within the core of the nucleus. So this would be the nuclear force. Part C, holds the nucleons in the nucleus. Well, as we just explained, the nuclear force only works inside the nucleus. So that would be where. Likewise, it's not going to be electrostatic force because protons, which are positively charged, aren't going to be held electrostatically to neutral neutrons. D, tends to make a nucleus unstable. And, well, the nucleus is being held together by the nuclear force, therefore the thing that must be trying to make it unstable is the electrostatic force. And this is something we deal with when we talk about quantum physics later on, is that because all the protons are positively charged, theoretically they should, through the electrostatic force, want to tear themselves apart, but the nuclear force overcomes it. Really simple question 1. So question 2. Complete the following radioactive decay equations. So it gives us 229 thorium with 90 protons, decays to radium plus an alpha particle. And for part B, it tells us that 6528 Ni, which I think is nickel, goes to copper plus beta plus a neutrino. So, or antineutrino. The first one, well, in alpha decay and beta decay, the first thing we want to do is look at what we're going to get on the alpha and beta particle, because that's always the same. It's the easiest one to remember. A beta particle is a helium nucleus, so we've got, if we call the black ones neutrons, 2 neutrons and 2 protons. So the proton number will be 2, 1, 2. The nucleon number will be 4. We should know this off by heart, but if we get in the test and we're not sure, that will always help us remember. And the beta particle, well, we know that a beta particle is just a little electron on its own, so it has no protons, but because an electron has a -1 charge and a proton has a +1 charge, we write it as a -1 on the proton number. It has no mass associated with it, it has no nucleons, so we have a 0 here. Now this gives us some indication as to what's going to happen then, doesn't it? Here we had 28, this side, we're gonna have to end up with 28 as a result of the bottom two numbers here. So we need something -1 to give us 28. Well, that would obviously be 29. And the top, well, nothing's going to change because it's a 0. Again here, the result of these two numbers must equal 90, so something add 2, which will be 88. And for the same reasons, the result of these two numbers must equal 229, so 225, and we take 4 off. Question 3. Let's move the paper up. Okay, question 3. The nucleus of the radioactive isotope of bismuth, and it gives us the details of bismuth, it's 21383, emits a beta particle, so we can draw along here, we're going to have a beta decay, we're going to have something here, and with beta decay we're going to get an antineutrino. It then emits an alpha particle. Now notice how I'm adding in the information I know as I'm reading it. And it's just a case of filling the blanks. And then another beta particle before becoming stable. Show that the stable nucleus is formed of a bismuth isotope. So theoretically what we should get here is bismuth. Now for bismuth to be here, well, what determines which element it is? Well, the protons determine what element it is. Therefore the proton number of bismuth, 83, must be where we end up with. Because if it was 84, it would be a different element. If it was 82, it would be a different element. So to end up with bismuth again, it must end up with 83 protons. So that's our first bit of the puzzle. Now, we don't need to know what these elements that we're going to run through in the decay in between are called. What I tend to do is call the first element I come up to X, and X will move to there. And then we're assuming we're going to have another element here, so we'll call that Y. Now we've pretty much got all the plots in place. It's just a case now of putting the numbers in. So here, as we've got a beta decay, well, nothing's going to change the nucleon number, but the proton number is going to have to go up 1, so that the total of these is 83. So we now have the values for our mystery element X. We can put that in here. We get an alpha decay, so we're going to lose 4 from this number, which is going to give us 209. So the total here is that. And we're going to lose 2 from this number, 82, so the total here is there. Now we have the values for our Y mystery particle, or element. Okay, now we know these are different elements than bismuth because this is not the same proton number. We had 84 protons here, 82 protons here. It'd be very easy to look them up in a periodic table to find out what them elements are, but that's just totally unnecessary for what we're dealing with. Our last change, well, we check that this is going to work. Do we end up with bismuth again? Well, we've got 82 here. The sum of these must be 82. 83 minus 1 will give us 82. So that is correct. We do get bismuth. And just to complete it, this top number isn't going to change, and we find that that's the answer. So you can see that the radioactive decay is actually giving us bismuth again, but a different isotope. This was bismuth 213, this will be bismuth 209. So a radioactive decay for a beta, then alpha, then beta has ended up giving us bismuth again, but a different isotope that's, as the book says, more stable. How many protons and neutrons are there in the nucleus immediately after it emits the alpha particle? Okay, so immediately after it emits the alpha particle, well, that will be mystery element Y. This is part A. part B. So mystery element Y, well, protons, 82. Neutrons, 209 minus 82, which is 127. Oh, that was part 2 of B. I've missed a bit. Bit out of order here. Part 1 of B says determine the nucleon number of this stable isotope. Well, we did that up here. It's 209. This is the new stable isotope. Okay, and the last question in this section. I'm not going to write these ones down, this is just more of an explanation. The neutrino hypothesis was put forward to explain beta decay. Explain what is meant by hypothesis. If you get questions like this in the exam, very simple to remember. Hypothesis is a theory that is untested. Okay, so important point. Theory, these are your keywords, untested. Okay. Part B, 1. State one property of a neutrino. Well, there's lots of properties you could explain. You could say that it doesn't interact with matter and etc. I always go for the easiest one to remember. With a neutrino, no charge. And last question on this section. Name 2 objects that produce neutrinos. Always good to know a couple of real world examples for where you find each type of particle. Common questions in the exam, they want to show that you've been taught how this actually works in the real world. Your go-to answers for neutrinos are the sun and nuclear reactors. Now if you can't remember, if you try and think about to actually detect neutrinos, they end up putting big water tanks next to nuclear reactors that with special water and special lights, and every now and again there's a tiny flash where one neutrino in 10 gazillion interacts with the water, and the sun is what produces most of the neutrinos that are going to bombard us on Earth. That is the end of that section.